So welcome back, and I've actually decided to make this a three-part lecture to give you a little break in between, because I understand I'm getting a little deeper into I'd say, science. So take a little break here and there. Okay, so we talked about specific humidity, which is specific humidity is a given mass of water vapor per given mass of air. And then saturation specific humidity is the specific humidity of the atmosphere when it is saturated. Slide 13, we have an index of water vapor content. We call it a mixing ratio, which is a measure of atmospheric moisture and the mass of water vapor per unit mass of dry air. It's usually expressed in grams per kilogram. And in a mixing ratio, it's very similar to specific humidity in that it expresses the mass of water vapor to mass of air. And the specific mixing ratio is very similar to the specific humidity. Okay. Maximum mixing ratio is the saturation mixing ratio. Alright, so just wrap your thoughts around that. It's the mass of water vapor per unit mass of air. Alright. Almost the same thing. Almost the same thing. Grams per kilogram. So we'll get that a little clearer. Now, the one that you're probably mostly familiar with, and you don't really realize how we attain this number, is in slide 14, relative humidity. I have to explain all those other slides in order to get to relative humidity. It's the amount of water vapor relative to the maximum that can exist at a particular temperature. So, relative humidity is actually the specific humidity given the saturation specific humidity. Now that turns out to be a decimal, which is less than 1. So we typically multiply it by 100. Okay, and that gives us a percentage. So percent relative humidity. It describes the amount of water vapor relative to the saturation point. It's a very uncomfortable point too when you have 100% humidity. See, in order to have 100% relative humidity, if you look at that equation again, you'd have to have specific humidity of 1 and a saturation specific humidity of 1. You got it? Or both the same. If it's 5 over 5, you get 1 again to get 100% relative humidity. So we're going to get to that. We're going to talk about that. Or it could be 0.01 over 0.01. Still get 1. So 100% relative humidity. The saturation point, or the relative humidity term, is relative to the air temperature and the total water vapor. Okay. Might not be easy for you to get your thoughts around it. So again, I might just take a quick break in a few slides so that you can attain that, maybe in about 5 or 6 slides. Relative humidity, slide 15. You got the coolest time of the day, which is usually right before the sun comes up. The relative humidity is the highest, and that's when the dew starts setting, so they must be related to each other. And then you got the lowest relative humidity when the sun is the highest. Highest that it's ever going to be in the day. It's not always high noon. Not always high noon, which you might think it is, but it's not. Temperature is dependent on other factors, moisture content of the air at different locations throughout the continent, or throughout northern hemisphere, southern hemisphere, and also it has different temperatures. So a lot of things going on regarding relative humidity. Meteorologists don't talk about all the variables regarding relative humidity. because they're just talking about local area usually, unless you start watching the Weather Channel. Then relative humidity takes a different, has a different meaning. It means more. So in slide 16, the relationship between relative humidity and temperature is expressed here. Notice as relative humidity increases, temperature decreases, and vice versa. Slide 17, dew point. Dew point might be one of the all-time hardest things for my students to understand. Relative humidity may be one of the easier ones. Dew point's hard. I don't know why. It takes a little time to get it, but let me help you. It's the temperature at which saturation occurs in the air. It's dependent upon the amount of water vapor present. Okay. You've seen fog. Alright, so what I want you to do is think of fog when I talk about dew point. Dew point and fog are related only at one particular time. When the right ingredients or the right variables are adjusted properly, you get fog. Now, how do you get fog, and what does the dew point have to do with it? I'll take you there, but let me back up and finish this slide off. High dew points indicate an abundant atmospheric moisture. Okay? Dew point is just a temperature. Degrees Fahrenheit, degrees Celsius. Okay? So what you can do is go online at the website I showed you at the beginning of class, or you can go on any other website and say, what is the dew point of San Antonio today? And it'll give you just a temperature. And that's the point where you can have condensation, moisture, dew, if the air temperature is equal to that temperature. That's all that means. So if saturation is reached, which is what I'm talking about, if the air temperature, saturation is reached, you know, we have relatively high humidity, we're getting saturated, and the air temperature cools further, water vapor is removed from the air through condensation. It doesn't rain, but it just appears on the ground, for example. So that's called dew. So when air reaches saturation at temperatures below freezing, we call it a frost point. So in other words, you reached a frost point. So saturation is where you get dew. Condensation is where you get dew. When the air temperature equals the dew point, you get dew. When you get fog, the air temperature drops below the dew point, so you're super saturated. A cloud forms at the ground. We call it fog. So dew point temperature in slide 18 gives you, there are some relationships, like the first part we have unsaturated air, and the next two parts we have saturated air. Okay, moving on. I'll tell you what, I'm going to take a break right now and we'll finish. I tell you, no, let's go a few more slides. I'm sorry. Thought we were going to take a break, didn't you? We're not. Let's go a few more slides. Alright. So let's measure humidity. It's measured by the use of the psychrometer, a sling psychrometer. You can look them up on Google, but you've probably heard of wet bulb and dry bulb readings. It's the same idea. It's got a little cotton wick. It's wet, attached to a bulb, and you got some thermometers. One's a wet bulb and one's a dry bulb thermometer. You swing the sling psychrometer, evaporation occurs from the wet bulb, which cools the bulb, and the wet bulb temperature eventually stabilizes. It allows the comparison with the dry bulb temperature. So you look up charts to help you determine the atmospheric humidity. Okay, and you look at the psychrometer for the depression, and you have other types of ways to measure humidity as well. But you and I just look on the web or we listen to the weatherman for humidity. Not humidity, but relative humidity. This is just measuring humidity. Alright? So, in that idea of identifying the humidity in the air, we can develop maps of the water vapor, the humidity in the atmosphere. We can develop it. And it's very interesting how you develop it. And it's very revealing when you overlay it over a continent, for example, over the United States. We can show you those water vapor maps next week, week 4, in global montage. Water vapor is supplied to the atmosphere by local evaporation or horizontal transport, which we refer to as advection. Slide 22 are processes that cause saturation. We have 3 ways. We have the addition of water vapor, mixing cold air and warm air, moist air by cooling the air to dew point. Saturation. Alright? Those are 3 ways. And they're added to the air to saturate. You got enough vapor, you cause saturation. And you could get fog. This is where you can chart the path of fog as a weatherman. You can actually predict fog in some respects. So with that curve on the slide 22, we'll move to slide 23 to talk about that curve, the effect of the curvature. Okay, small drops exhibit greater curvature than the larger drops. The curvature influences saturation vapor pressure with highly curved drops. So very small drops require supersaturation of over 200%. That's supersaturation. Hygroscopic water attracting aerosols. We have other things in the air. They act as condensation nuclei. You may have heard of acid rain. Particles in which water droplets form. Bigger water droplets, as a matter of fact. The condensation onto the condensation nuclei, it's called heterogeneous nucleation. And it dissolves the aerosol, so it may reach a solution, if you will. And you can look at a water droplet, slide 23, and see the effect of the curvature with the foreign material. And it causes saturation to increase. This is what we what we can refer to as cloud seeding if we intentionally make a bigger drop, cause condensation to occur faster. And because of that solution in slide 25, evaporation from solutions is lower than the pure water, so it's impure water. So less evaporation, more condensation. You get rain faster, and it opposes the curvature influences in a way that condensation typically occurs near 100% relative humidity. And in those hygroscopic nuclei, they're abundant in the atmosphere from many natural resources, because we have salt, we have dust, we have ash, etc. And then we have anthropogenic sources such as combustion, smog, if you will. But these small condensation nuclei lead to very tiny water drops. So the larger they are, we get what you might refer to as acid rain. But if they're very small, you get haze or smog, if you will, as a result. It's an increased vapor pressure, if you will. So the smaller the droplets require higher relative humidity to remain a liquid, or else you get haze. Okay? Now let's let's take a break right now, and then we're just going to finish it in for part 3.